Dear first year, first semester students of Department of Physics, Shahjahan University of Science and Technology. My dear students, today is my 11th lecture and 4 of my lectures are already in YouTube. I hope you have seen those. Try to concentrate on the topics I have discussed in the lectures that are found in the YouTube. So in this era of internet, YouTube is not something which cannot be accessed by you. You can easily access YouTube, and so try to access YouTube and find my lectures. You have to go first to SUST Physics, then you will find all the lectures I have given so far within 2 weeks. I have given 4 lectures or 4 videos are available now in the YouTube. Today is my 11th lecture, and today I shall discuss very important 2 things. Actually, one thing which is potential energy. Already we have come across kinetic energy. What is kinetic energy? Kinetic energy is the energy of motion. Then what is potential energy? Potential energy is called the energy associated with configuration of a system. What is configuration? What do you mean by configuration? Configuration is something that defines how the components of the system are arranged or located with respect to one another. Say, I have a triangle. You can put 3 particles at the tips of the triangle. Then this is a particular triangle configuration. You can also take a rectangle, and you can put 4 particles at the tips of the rectangle. Then this will be another configuration. So a configuration is nothing but a system, and within the system how the particles are arranged and located. So potential energy is defined for systems which has a particular configuration. And in other words, potential energy is associated with the configuration of the system. So this much for potential energy for now. Now, to define potential energy quantitatively, we have to go through a process. That process is nothing but we have to know first what is conservative force. If you do not know conservative force, you cannot appreciate the utility, the usefulness of potential energy. First, you have to understand what is conservative force. So I am going to discuss about conservative force first. We shall discuss conservative force with 2 examples. You know, if you do not have example, you cannot understand anything. Everything in the universe are known by examples. What scientists find, they find those through examples. So we shall take 2 examples. Number 1, the spring force. Spring force. Number 2, gravity. Using these 2 forces, spring force and gravity force, we shall discover what is called conservative forces. Okay. I begin by drawing details of a picture for the conservative force case. Conservative force for the spring case. Spring force in action. Say I draw this line and for this line, this is situated at x equal to 0 and here is the line. This is the x direction. Say this point is x equal to plus d and this point is x equal to minus d. Okay? Say a spring is in relaxed position. At that position is x equals 0. A spring is in relaxed position and that position is x equals 0. That is here. Now an external agent like us pushes the spring. Actually a block is associated with the spring. You cannot push a spring by your hand. You will be hard. But you attach a block with the spring and then press the block, you do the displacement. So I have a block here. Here I have a block. And some external agent compressed it to the location x equal to plus d. X equal to plus d. So what? And the spring is where? Spring is here. The spring is here. And it is attached with a heavy wire. So external agent compresses the spring through the block by a distance d from x equal to 0 to x equal to d. Okay? Now we shall begin our calculation by taking time t equal to 0 when the external agent withdraws its force. In this example, t time equal to 0 when the external agent stops working. When then will work? What will work? The spring will work. Because the spring is compressed, now the spring will work. It will push the block toward in this direction. So the next picture is x equals 0 You see, the spring pushes the block to x equal to 0. This is figure A. We shall not calculate any work for this figure. For figure 1, we shall not calculate any work because external body works here. But we want to find the force done by the spring. So our calculation will start from this figure. Here the spring working. How? The spring pushes the block from x equal to d to x equal to 0. Okay. When the spring pushes the block, what happens? The kinetic energy of the block increases. Whenever you do a work on a body, it is the last lecture, you surely remember what I have said in the last class. Whenever a work is done on a body, the body acquires kinetic energy. So whenever the spring pushes the block and pushes up to the point x equals 0, in this section, the kinetic energy of the block will increase. So it will not stop here. It will come say up to point x equal to minus d. So the next figure will be here the block Okay. The next figure will be the spring is now towards stress. So the spring is now towards stress. Now the force will be the force will reverse in its direction, and the block will come to here. Then what will happen? For kinetic energy, due to kinetic energy, the block will come. There will be 5 pictures. 1, 2, 3, 4, 5. I have done the right thing. You see, there will be 5 pictures. B, C, D, E. B, C, D, E defines a complete cycle. Execute figure A. Because in figure A, the spring force does not work. Actually, the external body compresses. In B, C, D, E, the spring works. It is a cycle. How the cycle begins? The cycle begins. The block is at x equal to D, comes to x equal to 0, then comes to x equal to minus D, then goes to x equal to 0, D, 0, then goes to x equal to plus D. So it's a cycle. From where it starts, it goes to where it is. In other words, it was the initial position, the final position is this. So this is a cycle. Now I want to compute the total work in this complete cycle. What is the total work in this complete cycle? For that, I shall use the formula for spring. Work done by spring. We have derived this formula in the last lecture. What is that? W equals minus half K x square minus xi square. Now I have the figure. I do calculate the works, and usually for B, what is the initial position for B? D. Initial position is D. Final position is what? 0. So W1 will be minus half K minus half K minus half K. Final position is what? X equal to 0, so 0 square. Initial position is what? Plus D square. Then minus plus half K D square. For C, W2 minus half K. I should not write every time this thing. For C, what is the initial position? X equal to 0, final position, x equal to minus D. So initial position is x equal to 0 square. Final position is minus D whole square. Then this gives nothing. This gives this square, you get minus half K D square. So you have going from 2. W1 is half K D square, W2 is minus half K D square. For D number figure, what is the initial position? Minus W3 equals minus half K. Initial position is minus D whole square. Final position is x equals 0 square. You get D square minus half K D square. This is W3, is it W3? What is W3? W3, the final position is x equals 0. The final position is x equals 0. Initial position is x equals minus d. So minus minus plus half the square. For E, W4 equals minus half k. What is the initial position? For E, what is the initial position? 0. Final position? D. So final position comes first, d square minus initial position minus half k d square. So you get half k d square minus half k d square, half k d square minus half k d square. So total work W net equals W1 plus W2 plus W3 plus W4 is equals 0, right? You get as 0. For spring force for a complete cycle, the total work is 0 done by the spring. We shall come now to the second example. The second example is the example of gravity. Say gravitational force, gravitational force in action. Gravitational force in action. Here is ground. An external agent projects a ball upward. What velocity v naught. So the initial kinetic energy Ki equals half m v naught square, right? Initial kinetic energy is half m v naught square. Now, since it has kinetic energy half m v naught square and the velocity is projected upward, it will go up and down. But gravity works downward, right? Gravity works downward, minus mg. Gravity works downward. The external agent projected the body upward, but the gravity works downward. So what will happen? The body will come, in the next figure I should draw this, the body will come momentarily at rest at x equal to y equals, we shall write it y direction, this is y direction, this is y equals h. So, after going up, the half of this naught square pushes it upward, but the gravity works downward. When these two become same, the body or the ball momentarily comes at rest at equals y equals h. Then what happens? The body falls to ground. The body falls to ground, right? So, in this case, the cycle has only two phases. The cycle consists of W1 equals 0 to h minus mg dy. Here dy will integrate to y, and when you put 8, it will give 8. When you give 0, it will give 0. So you will get minus mg y. This is W1. What is W2? In W2, again, the gravitational force acting downward, dy, but initial point h, final point 0. So when you do the integral, this will be y, 0 minus h minus plus, you will get mdy. W net equals W1 plus W2 equals 0. So you see, gravitational force, in case of gravitational force, the net work is done, which is 0. In these two examples, we find the important thing that for a complete cycle, the total work is done by the force, that means by spring force or gravitational force, or spring force or gravitational force. The total work done is what? Is 0. So we define conservative forces for this. For a complete cycle, if the total work is done 0, then the force is called conservative forces. So we write the definition. Consider the total work done by a force that acts on a particle as the particle moves around a closed path and returns to its starting point. If this total work is 0, we call the force a conservative force. Otherwise, it is not. My dear students, I have a very important business for now to do. So today this much. In the next lecture, I should deliver to you the concepts and the related equations for potential energy. So stay home, look at the videos found in the YouTube and learn what is I am delivering to you, what is I am teaching to you. I wish you a good health and a good career in life. Thank you very much.